Chapter 2: Vectors, Matrices, and Determinants. Learning objectives of this chapter are beginning to understand the vocabulary of mathematics and programming, an introduction to the most important tools of linear algebra, vectors and matrices, and to find out an easy way to determine when a system of linear equations has a unique answer. The outcomes are knowing the difference between scalars and arrays, row vectors and column vectors, rectangular matrices and square matrices, some new mathematical notation, and finally, learning how to use matrices and vectors to express systems of linear equations. Scalars are simply numbers you've been using for a long time. You see some examples of them. In Julia, we can define them by assigning a number to a variable using an equality sign. Here you can see that I'm assigning some numbers to a set of variables and then printing them in the last line. Arrays are scalars that are organized into lists. The list could be rectangular or square. It can be made of columns of numbers or rows of numbers. If you've ever seen a spreadsheet, then you've seen an array of numbers. In Julia, we can define, for example here, a 1 by 5 array of numbers by using a space to separate numbers and assigning them to variable A. To define a column array, here a 5 by 1 array, we can use comma to separate the numbers. Or we could use semicolon to get the same result. And here the result is a 5 by 1 array. The last example, B and C are equal. To check that, we can use two equality signs to check if the left hand side and right hand side are equal, which you can see here. The output is true, meaning B and C are equal. For us, a vector is a finite order list of numbers. A row vector has one row and multiple columns. For example, here V has one row and 3 columns, and we call it a 3 vector. A column vector has multiple rows and 1 column. Here V has 3 rows and 1 column. We call it the column 3 vector. In general, if the vector has n entries or elements, if it's a column n vector, we can write it in this form, and if it's a row n vector, we can write it here. Notice that there is an order in the entries of vector v, meaning v1 defines the location of v uniquely, and vn meaning that this number or variable is located at column n. Matrices are generalizations of vectors. For example, here we see a 3 by 2 matrix. We have 3 rows and 2 columns. In Julia, we can use a space to define each row and then use comma or semicolon to move to the next row. This way we can define, as you can see, a 3 by 2 array. Another example, here you see a 2 by 3 matrix. Similarly, we can use a space and semicolon to define the 2 by 3 array. A rectangular matrix of size n by m takes this form. We have n rows and m columns. And if it's a square matrix, we have the same number of rows and columns. And we call it, for example, here an n by n matrix. We have n rows and n columns. We use this notation, A subscript I and j, to show the element, the entry of the matrix A that lies in the intersection of ith row and jth column. This way, uniquely, we can locate Aij. For example, A22 means second row, second column, and we can locate it uniquely inside the matrix. The diagonal of a matrix is a vector that is defined by picking the elements of A that lie in the diagonal, meaning they have the same subscript for the row and column numbers. Sometimes the diagonal is called the main diagonal of the matrix. What about the other elements? Let's just call them off diagonal. Next time we'll talk about linear systems of equations in matrix form.